Hey guys, welcome back to General Chemistry. We are going to dive into more of Chapter 3 in our textbook. We're going to talk about orbital diagrams. So up until this point, we have talked about electrons, the fact that they are located outside of the nucleus in what we called a cloud, quote unquote. And then in previous lectures, we talked about quantum numbers. So we talked about the fact that these electrons live in very distinct houses, if you will, and each of those has a 4-digit zip code that gets us directly into that location. So it could live in the second energy level. It could live in an s orbital, so sphere-shaped orbital. And then it could live on the top floor, so the spin quantum number could be -1/2 or +1/2. So that was talking about the houses that they live in. What we're going to do now is we're going to talk about how these electrons file into those houses. So they don't just get to randomly pick which one they want to live in. There's a very structured way in which these electrons kind of file into their home. So that's what orbital diagrams is going to lead us into. Orbital diagrams is a training tool that we're going to use. Eventually, we are going to get rid of this training tool and go straight into being able to do this using the periodic table. So I like to think of orbital diagrams as kind of like training wheels. So eventually we want to take the training wheels off and ride the 2-wheel bike, but it's always a good idea to start with training wheels. I think that's a safe choice. So orbital diagrams. Electrons, so I said this is a very strict set of rules. So the first rule that we're going to talk about is something called the Aufbau Principle. So the Aufbau Principle tells us that electrons are placed in the lowest energy level available, and that each orbital can only have 2 electrons, no more. Okay. So just like us, electrons are lazy. So when an electron walks up to a particular element and it says, all right, I want to find a house to live in, he's not going to climb up to the 5th floor and find a house up there in the 5th floor. The electron's going to find the lowest energy level available, or the lowest energy orbital available. So here we see our orbital diagram, which is going to teach us what the lowest energy available looks like. So down here at the bottom, we have low energy. Up here at the top, we have high energy. So we look at the very first house or orbital that is available to us, and that's going to be the 1s orbital. So that is the orbital that is in the lowest energy level. So the energy level is 1, n equals 1. And then the s orbital is the easiest one to get into. It's a simple sphere, so it's not a lot of chaos to get into that one. The next orbital then we would go to, once that one is filled up, is the 2s orbital. So now we're in the second energy level. We still start with the s orbital, or the sphere. That's the easiest one to get into. And then the next one that we would go to is the 2p orbital. So we're in the second energy level. Now that the s orbital, the sphere, is filled up, now we can go to the p orbital and we can decide how we're going to fill this up. So if you guys remember back to quantum numbers, these things line up very nicely. If you think back to quantum numbers, remember there was 3 ways to orient a p orbital in space, like the up and down, the side to side, coming out at us, going back into the screen. So 3 different ways to orient that p orbital. And here we see 3 different orbitals that we can fill. That is very much related. That's exactly what those 3 lines are standing for. So 1s, 2s, 2p, and then we would just continue on in this diagram until we fill up the orbitals, or until we run out of electrons that we're trying to give away. Okay. This is another orbital diagram. I chose this one first because this is from your textbook. I like this one better for multiple reasons. 1, it's colored. Colors are pretty. 2, it is boxes, so I find that a little bit easier to write in. And then lastly, I think this does a better job of helping you decide what comes next. It's stacked right on top of each other, where as you go up here, things start to get a little crazy up here. And it's not very intuitive what's going on. This one's a little bit more intuitive here. So I like this one. All right, so now would be a great time to pull out a periodic table if you don't already have one right next to you. So we're going to start looking at how we fill in these orbital diagrams. So one of the things I want you guys to remember is the fact that, these elements for right now, we're going to assume that they're neutral elements or neutral atoms. So what that assumption does for us is it allows us to predict the number of electrons. So if it's a neutral atom, the number of protons and the number of electrons are equal. So when we start talking about a particular element, we can assume that the number of electrons is the same as the number of protons. Okay. So let's do the orbital diagram for the easiest element there is on the periodic table. Let's do the orbital diagram for hydrogen. Okay. So looking at your periodic table, we see that hydrogen has one electron. So we have one electron to find a home for. One proton, one electron, that's neutral. So Aufbau Principle tells me that the electrons are going to fill from the lowest energy level to the highest. So here's my 1s orbital, and there's an electron that's going to go into that 1s orbital. We typically draw electrons as half arrows, so this is how I depicted that first electron. Remember, we can have up to 2 electrons in each box. So when we start putting 2 electrons in the box, the next electron would look like this. So remember, we have that spin, magnetic, negative, minus, negative 1/2 and positive 1/2. So somebody lives on the top floor, somebody lives on the bottom floor. And that's how we symbolically represent that or depict that. Okay. So here's the orbital diagram for hydrogen. It has 1 electron, and that 1 electron is in the 1s orbital. Okay. Let's do another example. Let's look at the orbital diagram for lithium. So how many electrons does lithium have? Lithium is the 3rd element on the periodic table. So that means it's going to have 3 electrons. Aufbau Principle tells us we're going to fill from the lowest energy level to the highest. And we have 3 electrons to find a home for. So the first electron is going to go into 1s. The second electron is also going to go into 1s. That orbital is now full. It has 2 electrons. It's full. I can't put any more in. So then we're going to go to the 2s, and we're going to put 1 electron there. So this is the orbital diagram for lithium. Right. Let's see. Yep. So let's do one more. I'm going to give you guys a couple minutes or a couple seconds to fill this one out. But why don't you guys do the the orbital diagram for, let's do nitrogen. All right, so how many electrons does nitrogen have? Nitrogen has 7 electrons. Okay. So the first electron is going to go into 1s. Second electron is also going to go into 1s. That's 2. The next one is going to go into 2s. So we've got 1, 2, 3, 4. Okay. So now we have 3 more electrons that we need to find a home for. 1s is full, 2s is full. Now we go to 2p. How many of you guys did this? Totally what I would expect you to do because you don't know any other way to do it. Okay? But let me propose the following scenario. Okay? Let's say you are going on to a 4-year college and you're picking a dorm to live in. And the RA was like, okay, going up to the 2nd floor. There's 3 rooms up there. You can pick any room you want. Doesn't really matter which one. Just tell me which one you pick. Okay. You walk up to the 1st room. Somebody's in there. Are you going to go ahead and walk in that room and say, meh, I'll partner up with you? Or are you going to go down to the next room and check that one out? You go down to the next room, you check that one out, it's empty. So which room are you going to pick? Are you going to pick the room that already has somebody in there? Or are you going to pick the room that's empty that doesn't have anybody in there yet and pray that nobody else shows up? Yeah, you're going to pick the empty room, right? Well, electrons are going to do the same thing. When the electrons go to fill a p orbital or a d orbital as we move up, they're going to do so in the following way. So they're going to first go in unpaired, okay? So for nitrogen, he had 7 electrons, so 1, 2, 3, 4, 5, 6, 7. That would be the end. So the first thing they're going to do is they're going to unpair. Now, if we had more electrons to find a home for us, let's say we were doing like fluorine or neon. Now, if we had more electrons to put in, then the electrons would go back and pair up before going to the next floor. Okay, but if given the option, electrons will go in as unpaired rather than paired. Same thing if you were picking out a new apartment or a new dorm room. If there's an ability to unpair and live by yourself, that's exactly what you're going to do. Now, this has a rule. It's called Hund's rule. So Hund's rule says that it is lower in energy for electrons to have the maximum number of unpaired rather than paired. So it's just a fancy way of saying if we can unpair, that's how we're going to do it. Remember that these particles are negatively charged. So cramming 2 negatively charged particles in the same box certainly is going to cause some repulsion between those particles, which would increase the energy. So that's one of the reasons that we say it is lower in energy to have unpaired electrons. So if we can put them in separate boxes, we will, until that's not an option anymore. Then they pair up. Okay. All right, let's do one more example on this slide, and then we'll talk about our last rule. So let's go ahead and do the orbital diagram for, let's do sulfur. That would be fine. I'll give you a minute to do the orbital diagram for sulfur. All right, sulfur has 16 electrons. It's a lot. So to find for a home for 16 electrons using our orbital diagram. So we're going to start from the bottom, and we're going to go 1, 1, 2, 3, 4. I know the p orbital is going to be full, but watch how I put these in. And this is going to help me remember Hund's rule. Remember that they go in unpaired. So this is how I always fill them up. So we've got 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So that would be the orbital diagram for sulfur. So we get up to the 3rd energy level. We're putting electrons into the p orbital, and we put them in 1, 1, 1, so unpaired first. Now, The last electron didn't have a choice. He has to be paired with one of them. So we put him in a box with another electron. So this would be the orbital diagram for sulfur. The last rule that's going to kind of dictate how these electrons file into their homes is something called the Pauli exclusion rule. So this just says that no two electrons in an atom can have the same set of quantum numbers or the same address. So this is why we draw one as an up arrow and one as a down arrow. For example, let's just kind of focus in here. Let's say those are the two electrons that we're looking at. So if I look at the address for those electrons, they're almost exactly the same until we get to the last quantum number. So both of those electrons are in the second energy level, 2 and 2. Both of those electrons are in an s orbital. So the second quantum number is 0 when we're in an s orbital. Only one way to orient an s orbital in space. So remember the next one is also a 0. So Pauli's exclusion rule says we can't have the same set of 4 quantum numbers. So what differentiates these two electrons? Well, it's the last one. So let me actually color code this so you can see it. So, and let me not use red green just in case anybody's colorblind. We'll use black. There you go. So the red arrow, if I do his address up here on the top, he's in the second energy level in an s orbital. Only one way to orient that, so that's a 0. And he lives on the top floor, so he has a positive 1/2 as his spin magnetic. And then if I go to the black arrow, we'll see that he's also in the second energy level in an s orbital. But he lives on the bottom floor, so his spin magnetic is negative 1/2. So that's all the Pauli exclusion rule is telling us, is that if two electrons happen to be in the same box, one has to be up and one has to be down. So that's it for orbital diagrams. This would be a great opportunity to practice some orbital diagrams on your own. After the orbital diagrams, we're going to take the training wheels off and we're going to talk about electron configurations. I hope you guys found this helpful.